Today is our first lesson on energy, and talking about energy, we're going to be talking specifically about work. And so a couple things to take a look at. First of all, over in the margin here, I'm just telling you about what are some of the variables. In the AP world, we use E for energy, we use K for kinetic energy, and we use U for potential energy. I do not know who chose U or what the connection is there, so I'm not sure why that's a U, but that means potential energy. But today we're not really talking so much about kinetic and potential energy, we're talking more about work. But we need to understand energy to get there. When you transfer energy from one object to another, that is called work. So if you have a system and you are adding energy to the system, or the system is losing energy, that is called work. In physics, a lot of times that might be friction. A system can go through, but the system is losing energy due to friction, so that friction is called work. Or another thing might be a force, like if you hit something, that's giving energy to it, and that is making it move. That is a force, but you've given energy through that force. So that is called work. The variable for work is a capital W. Now, later on when we get to a different unit, we will use W to stand for watts, but we are talking in this unit about work. So W means work here. If you look over here in the text box, these are the equations that are given to you in the textbook. F sub x times delta x, or F cosine theta times delta x. But down underneath the text box, I have written out how they are written on the AP sheet. The first part, they have the work is the force which is parallel times the distance. So force and distance have to be parallel to each other in order for it to be considered work. But then it's just force times distance. Or if they're not parallel, then you do force times distance times the cosine of theta. And that cosine theta is going to give you the amount in the x direction, or whichever direction you're going. Okay, so that's explained here, where F cosine theta is the component of the applied force parallel to the direction of motion, and delta x is the magnitude of the object's displacement. So it means how far it went. Okay, a couple things. Work is a scalar. It does not have a direction. Even though the direction has to be parallel to the force, work itself is scalar. And the SI unit of work is called the joule. And a joule is congruent to a Newton meter. So Newton meter is the same as a joule. All right, let's take a look at our first example. First of all, there's a few things I left off of the diagram. So if you can show that this vector, and let's make it a vector, this vector is 50 newtons, and then this is 30 degrees. The problem, use the following diagram to determine the distance the block was pulled if the work done on it was equal to 1.2 times 10 to the third joules. Assume there is no friction acting on the block. So we want to take the force which is parallel to the motion. So if the motion is going in this dotted line direction, then that's the part that we want. We don't want the whole 50, we only want the component which is parallel to the direction. So let's go ahead and plug in what we know. We know that the work is 1.2 times 10 to the third, which you can call 1.2 times 10 to the third if you want to, or if you just move your decimal over 3 places, you can also call that 1,200 joules. And that should be equal to the force in the x direction times how far it went. And the question is, how far did it go? The force in the x direction is going to be F cosine theta. I might just write that here, but that's going to be F cosine theta times delta x. So F cosine theta, well, our F is 50 newtons, and then we're going to have cosine of 30 degrees. All we're doing is finding this x component of the force, and then multiply that times the change in x. That's what we're solving for, is how far did we go. At this point, make sure you are in degree mode, and we're going to take that in degree mode. So if we do that on our calculator, 50 times the cosine of 30 is 43.3, and that's still in newtons. And then we'll divide both sides, divide by 43.3, and we get 27.7 you're going to get joules over newtons. But remember, joules is a newton meter. So that's like newton meters over newtons. So the newtons will cancel, and so we get as an answer 27.7 meters. That's how far it traveled. That's just an example to show you how to use the equation. Let's look at another example. A 55 kilogram box, I left out the word box, a 55 kilogram box is being pushed a distance of 7 meters across the floor by a force P whose magnitude is 150 newtons. The force P is parallel to the displacement of the box. The coefficient of the kinetic friction is 0.25. Determine the work done on the box by each of the 4 forces that act on the box. Be sure to include the proper plus or minus sign for the work done by each force. All right, so first of all, let's start off talking about our vertical components. We have our box. We're going to draw our free body diagram. We have the gravity acting downwards, the normal force acting upwards. We have the force called P going to the right. I made mine go to the right. We have the force of friction going to the left because the friction has to oppose the applied force. So first of all, the question was asking about all 4 forces. So we have 4 vectors here. We're going to find the magnitude of each of them. Well, the normal force and the gravitational force, how much work are they doing? Well, the box is moving this way. And so the normal force and the gravitational force are not doing anything as far as work goes because they're not going in the same direction as the movement. And so there are 0 joules of work done by the normal force and 0 joules of work done by the gravitational force. All right, well, there is horizontal movement, and so we do need to take a look at what's going on horizontally. Well, the work being done by the force P is force times delta x. And so if we read our problem again, our force, I'm going to WP equals the force, which is 150 newtons, and the distance, which is 7 meters. And we just need to multiply that out to get our answers. So WP, the work done by the force, by the pulling, is 1,050 joules. So that's a real basic way. You just have to plug them in. How much work is done? Well, how far did it go? And what was the force? That gives me the work. Let's look at the next part, which is how much work was done by friction. That equation is going to be the force of friction times distance. That's what we always do. We take our force times our distance. Well, the force of friction is mu sub k times the normal force. And we're going to take all of that and multiply it by delta x. Well, mu sub k, we were told up above that mu sub k is 0.25. Our normal force is gravity times mass, or mass times acceleration. So that's 55 kilograms. And it is going at 9.8 meters per second squared. That's for gravity. This time I have it positive because I'm talking about normal force. Normal force is going upward. It's opposing the gravitational force. And then our delta x, well, our delta x is 7 meters. And so now, to find out my work done by friction, all I have to do is plug that into my calculator. And I plug that into my calculator, and I get 943.25. Now, we do need to decide which one's going to be positive, which one's going to be negative, because they're going in different directions. And typically we call going to the right positive, so let's call this one going to the left negative. So our friction work is going to be negative. In this case, we have work being done to push it to the right, but there is also work being done that stops it, the frictional force that kind of impedes it going to the left. And so those two are going to oppose each other. Now we could find the net work by subtracting those two, or in this case adding those two. If we added those two together, that would give us the net work. That wasn't part of the question, but I just want you to understand that this is going to the right, the second one's going to the left, and so to find out the net, you would subtract the absolute values of those. Let's go ahead and turn the page. Okay, so we've mentioned energy, and we need to talk some about energy. The SI unit of energy is the joule. That's just another unit that you need to get to know. Energy units is joules. That's the same as it was for work. Work is also in joules. So when work is done on an object, energy is being transferred to the object from whatever is performing the work. Or it could be that energy is, you're losing energy in the case of friction or etc. So that's why over the margin I'm mentioning that work is transferred into energy. Again, whether it's losing energy or gaining energy, work is transferred into by energy because those are joules, and it's the same joules all around. As far as kinetic energy, another abbreviation, the book uses KE for kinetic energy. The AP just uses a plain K. So just so you know that. All right, we need to talk about mechanical energy. We have different kinds of mechanical energy. We have kinetic energy and we have potential energy. There is a third form that I also should mention probably, and that is called spring. So we have mechanical energy, which is broken down into kinetic energy and potential energy. Kinetic energy can be translational, that is linear, or rotational, going in a circle. In this unit, we are focusing on the translational. Later, we will talk about rotational. As far as potential energy goes, there are two forms of potential energy that we are going to get to. There are other forms, but we're going to talk about gravitational potential energy and elastic or spring energy. And if you just think about that, like if you have something, you're holding something above the ground, it has energy because it can go, right? It's going to go to the ground. So that's gravitational potential energy. Same thing with a spring. If you compress a spring, before you let it go, it has some potential energy and it can hit something and make something go. So that is energy. Okay, kinetic energy specifically is a form of mechanical energy that is contained in the motion of an object. The translational kinetic energy of an object is calculated using this equation. This equation is the same equation from the AP sheet as it is from our textbook. And this is an equation that, no, you don't have to memorize it, but I think you're going to, because we're going to use it so much that you're going to know that K equals 1/2 mv squared. It's just going to come naturally to you because we're going to use it so much. So m is the mass and v is the velocity. Notice that we are squaring that velocity, and so we need to think about the relationship between the mass and the kinetic energy and the relationship between the velocity and the kinetic energy, and we'll talk about that. The third concept is the work energy theorem, and so let's talk a little bit about that. The work energy theorem talks about net work, and that's a little bit about, I started to talk about that on the previous page, the net work done on an object. And the net work is the final energy minus the initial energy. That gives us net work. And so we still have the same equation. I kind of wrote this part going to the left, this part going to the right. That is, going to the left, we have F net times delta x. That's work, force times distance. And then on the right, I wrote it out in different terms, 1/2 mv squared for final minus 1/2 mv squared for initial. So in other words, you can use any part of this equation that you need to and kind of put them together in pieces that you need to put them together with. Over in the margin, notice that the net work is the change in kinetic energy. So if you have a change in kinetic energy, that's because you had work. Maybe you had work added to the system, or you had work that was lost from the system. That is a change in kinetic energy. So, and just a little note, it's kind of saying the same thing. The work energy theorem results from a net force acting on an object. Okay, question 3 says, examine the work energy theorem and determine how the net work done on an object is related to the object's kinetic energy. Well, actually, that is where that comes in, okay? Okay, let's look at an example here. It says, notice that as work is performed on the crate in the following diagram, energy is transferred to it and becomes kinetic energy. So in other words, if the box is just sitting there, it doesn't really have any energy. But as you move it, it starts to have velocity. And the equation says if you have velocity, you have energy. And so just sitting there does not have much energy. You start moving it, it has more energy. So let's look at number 4. It's going to relate back to this diagram. If the crate in the preceding diagram has a mass of 25 kilograms and is pushed with a force of 40 newtons over a distance of 20 meters, what would its final speed be equal to? Assume there is no friction acting on the crate. Okay, well, out in the margin, I took a minute to write down some information that was pertinent information. I guess I also need to write down that the delta x is 20. So we're going to use this information, we're going to plug it into our equation to find out the velocity. So our net force is 40 newtons. We are given that, that is 40 newtons. And the distance traveled is 20 meters. And again, those are parallel. It's going straight across. There's no angles involved, so we don't need any cosine. On the other side, we have 1/2 mv squared minus 1/2 mv squared. And realize that the initial velocity is 0. It's just sitting there. So we don't even need this because that's all 0. So really all we need is the 1/2 mv final. And the mass is 25 kilograms. And the v, that's what we're looking for. So now we just need to take a minute to simplify this a little bit and see what we get. So we put this into our calculator, or we can do this one in our heads. We get 800 Newton meters over here, and we get 12.5 kilograms. A Newton meter is a joule, so we can change that to joules. I'm going to leave it as a Newton meter for now, because remember that also newtons are kilogram meter per second squared. And so what we really have is kilogram meter squared per second squared. I'm just doing this with the units so that by the end we can see where our units have come from and if we are accurate. Because we're going to divide by 12.5 kilograms. And when we divide by 12.5 kilograms, the kilogram unit gets lost. And so 800 divided by 12.5 is 64. And the units that we have left, meter times meter, is meter squared per second squared. And over on the right, we have the velocity squared. So now we just have to take the square root of both sides. And so what we get is 8 meters per second. And so we've solved for the velocity. It again says assume there is no friction. So we don't have any other force acting to the left. We just have the positive going to the right. We used our equations. We did not have any initial velocities, that got canceled out. And our final velocity is 8 meters per second squared. Question number 5 is a two-part question. Let's read through it, see what we're looking at, and then we'll attack it. The force is now removed from the crates. We're dealing with the same crates. The force is now removed from the crate and is allowed to come to rest after sliding 12 meters along the surface with friction. What is the work done on the crate by the frictional force? And what is the coefficient of friction between the floor and the crate? So out in the margin, I have that our distance is going to be 12 meters. Our mass is still 25 kilograms. The velocity, that's the velocity that we just figured on the other side. That's where that 8 is coming from. It's from the other side of the paper. We figured that it was 8 meters per second squared. And we want to know if it's going to come to a stop. So when it comes to a stop, then that's going to be 0 meters per second, right? Question A, what is the work done on the crate by the frictional force? Two ways to think about this. The more basic way is on the other side, we had this diagram where this was our force and this is our friction. We'll call this our pulled force. Well, as they are moving from here to until it stops, I hope you can see what that's going to be, that if there were 800 joules, but then it came to rest, we're now down to 0 joules. So it went from having 800 joules now down to 0 joules. So let's take a look at what's going on. We couldn't think that through maybe, and we needed an equation for it. Well, the net work is going to be the difference in kinetic energy. The final, we just said a second ago, the final energy was 0, so that's gone. So we really just have the initial energy of how much that is. Notice we have this minus sign. Let's not forget that negative sign. And so our net work is just 1/2 times the mass, which is 25, times the velocity, which we figured from the other side was 8. And now we just need to multiply that out. And so we multiply that out and we come up with negative 800 Newton meters, or in other words, negative 800 joules. So let's think about that, and does that make sense? From what I was saying a minute ago, we had 800 joules to start, and that was from the previous page. We had 800 joules to start. We then lost all of it, And so we lost 800 joules. Right? On the other page, do you see where I'm getting this 800 from? We had 800 because we took 40 newtons times 20 meters. So it had 800 joules stored up in it before it was let go. Has that 800 joules. We then let it go. It comes to a stop. It loses all 800 of those. So part A, the work done, is 800 joules. That is basically friction took 800 joules away from our system, because friction turns into thermal energy, and thermal energy is dissipated. And so when it's dissipated, we don't have it anymore. Okay, part B, what is the coefficient of kinetic friction between the floor and the crate? All right, originally on the other side, we said let's assume there is no friction. Well, now they're changing it up and saying, well, actually there is friction. Maybe like it was pushed along during the no friction part, and then once it hits the friction, we give that force away. Now we have friction. Well, how can we set this up? Let's think about using our basic equation. That is our net work equation. So that should say net force times delta X. Okay, our net work done is negative 800 joules. Negative 800 joules. Our net force, well, the net force we're talking about is we're talking about the friction. So let's make that a frictional force. The frictional force is acting in the negative direction. So I'm going to call this a negative frictional force times the distance traveled, which is 12 meters, right here, 12 meters. So I'm going to divide by negative 12. And when I divide by negative 12, I get that the frictional force is, I'm going to call it kinetic friction. The frictional force is 66.67. I'm not there yet, but I've solved for frictional force. Well, I also know that the equation for frictional force is mu times the normal force. And so I can put my 66.7 over here on the left, and I'm solving for mu, that's what I'm looking for, and my normal force is 25 times 9.8. 25 again, 25 kilograms, and 9.8 is gravity, but this time it's the normal force, so it's acting upwards. So if we take our 66.7 and we divide by 25 times 9.8, we get our mu, and that comes out to be 0.272. And this is kinetic friction. So these new formulas that we have, we just have to become more comfortable with them. When do we use them? Which one should we use? So that's what we're going to continue practicing on in this unit.